It's Sunday, the 12th, and we're winding up week 5, your midterm. I see many of you have finished. Some are still haven't submitted yet. Uh, Hopefully, you will get them all done tonight. Uh, and this video is focused on week 6. I'm calling it In Week 6, an introductory video. It's up there with the overview. If I was you, I would definitely pay attention to that video. You have an assignment in week 6 that I'm going to focus on in this video. So if you're paying attention, you'll probably do well on the assignment and not have to spend a whole lot of time on it. Anyway, that's my purpose, and I hope it works out that way. So this week's 6 assignment has, I think, about 5 questions, and they're all pertaining to soils. Uh, I'm struggling with uh, the tailgate. I'm wrestling with how I want to do that. So I hope you come to the video first and you hear this, then I will get the tailgate up. I just want to make it worthwhile. Also, if I have a chance, I'm going to put in I may use a tailgate for what we call group index. And to do group indexes in the AASHTO system, which also have to be done, you've had a little bit of exposure or will have some exposure to what the AASHTO chart looks like. But to cut this thing, not take up too much time talking about it, so order of operations is what I'm getting up to when you have a bunch of parentheses and brackets and parentheses and brackets and what to do first, when to do it. You all probably have been exposed to PEMDAS, they call it. And these are the order, it's an order of operation. Like the P is for parentheses, get rid of all of your P's. I'm sorry, get rid of your parentheses. Okay. The next step will be exponents, if you have exponents. And so far, we don't have any exponents. Get rid of those. Then it comes the D is dividing, and the A is addition uh, and subtraction. The DAS, division, addition, and subtraction. So parentheses is usually indicated by multiplication. You need to work from your left to your right when you're doing these things, and you will see what I'm talking about when you get on into 6. It's just like uh, you'll encounter this. It would be great if we required algebra, but we wouldn't get this is not this comes from algebra, but it's not going to be hard. It's just something I want you to learn to do. A lot of the things in this soils course are beyond the scope of an operator, and on purpose, because I still want to remind us all that I think we're all here to become first line and upper echelon managers at some point. We're career minded, I think. Uh, so here we go. Uh, where am I? Okay, I have my ebook up, and I'm in chapter 1, the very beginning, introduction. If you go down, it talks about soil being more or less taken for granted for by average person, but to us, uh, we're deeply concerned, as the book calls it. Engineers, as well as geologists, contractors, hydrologists, farmers, agronomists, and soil chemists, and others. So, and the reason being is in construction, most structures of all types rest either directly or indirectly on dirt, on the soil. And proper analysis of that soil and design of the structure's foundations are necessary to ensure a safe structure free of undue settling and or collapse. A comprehensive knowledge of soil in a specific location is important. The study of soils should be an important component in the education of civil engineers, for instance. We need to know about soils. Why is it important? It's because that's what everything sits on. We're the first uh, level of construction on most projects. Chapter 1 will relate the information of natural soil deposits and describe some surface soils. We will be getting into Chapter 2, and that's when we get deep into the AASHTO classification. It introduces and defines various engineering properties. Now, Chapter 2, I'm not sure what I want to do with it. You probably it's it's it doesn't talk much about shrink and swell, but most of the stuff in chapter 2 in the beginning, the first couple of pages, maybe 3, are things that you have been exposed to, I'm sure. So we'll just briefly fly through it, but the remainder of chapter 2 is when we start learning how to gather informations, how to not tabulate, but calculate the results of the sieve analysis so that we can eventually come up with a soil size distribution uh, chart, which curve really is what it is. So back to rocks. Uh, the sources of soil, that's where soil comes from, rocks. It says soil is composed of particles large and small, and it may be necessary to include as soil not only solid matter but also air and water, because all soil has three uh, uh, components: air, water, and let's just call it dirt, whatever mineral. So I'm not going to spend much time on this phase. Let me see before I go. And here we start first talking about rocks, the types of rocks, and jump up here to uh, what is this? Throughout, let me read this. Soil is composed of particles large and small, and it may be necessary to include as soil not only the solid matter but also the air and water that is in soil. The particles are a result of weathering of rocks, degeneration and decomposition of rocks, decay of vegetation. Some particles may, over a period of time, become solidated under the weight of overlying material and then back to rock. So there's a geological uh, circle, I guess I'll call it till the name comes to me. But we go from rock to soil, and then through time and pressure and weathers and things, we go back to rock. Uh, Up here, we'll start out with rocks. They're saying rocks can be classified into 3 basic groups that reflect their origin and our method of formation: igneous, sedimentary, metamorphic. You need to know those. Igneous rocks form when magma, molten matter, such as that produced by erupting volcanoes, cools sufficiently to solidify. A lot of the mountains in Colorado are actually lava flows that stopped. It goes on to say that volcanic action, normally referred to as volcanism, can occur beneath or upon the Earth's surface. They probably produce the minority of Earth igneous rocks. However, during the Earth's formative stages, I can let you read this, continue on about igneous rocks. They can be coarse grained or fine grained. That's their composition, either coarse or porous or fine type, depending on whether cooling occurred slowly or rapidly. Relatively slow cooling occurs when the magma is trapped in the crust below the Earth's surface, such as at the core of a mountain range, whereas more rapid cooling occurs and the magma reaches the surface while molten while still in the lava flow stage. Of the coarse-grained igneous rocks, the most common is granite, a hard rock which is quartz, widely used as a construction material for monuments, and you've seen those in many cemeteries, I'm sure, and statues. Others are syenites, diorites, and gabbros. I'm not sure where they came from, where that comes from. I don't think that's on the test. The most common of the fine grained igneous rock is something called basalt, and I think that I left it out. I think I didn't want to include it in the rocks as we go on in here. But it's a hard, dark colored rock rich in iron or iron combination of magnesium mineral, ferro is iron, and often used in road constructions. Uh, Rhyolites and andites, I don't know. Being generally hard, dense, durable, igneous rocks often make good construction material. Also, they typically have bearing capacities. I'll try not to overread this as you have your own book, but I want whatever I'm bringing up for the most part you might be aware of. Let's see. Sedimentary. Those are rocks compose the great majority of rocks. They're found on the Earth's surface. They're formed when mineral particles, fragmented rock particles, and the remains of certain organisms, including us, I think, are transported by wind, water, and ice. With the water being the predominant transporting agent, what about sedimentation? Creeks, construction sites, right? That's all part of it, the sediment, and all part of this geo circle thing that we'll get to in a minute. But that's a transporting agent. You'll learn as we go on that wind is also a transporting agent. Look at the Mississippi River, the mouth of the Mississippi River, where New Orleans is. That's all sediment from the river. That's kind of flowed and filled and flowed and filled and filled until, have a landmass down there. Over a period of time, the layers accumulate at a site. Pressure on lower layers resulting from that weight of overlying strata hardens and the deposits forming sedimentary rocks. So under the water in New Orleans, you've got some layers of sedimentation, and some down on deeper according to this, have turned into rocks. The most common sedimentary rocks are shale, sandstone, limestone, and dolomite. Don't think that's on the test. Sandstone, now we're still talking about sedimentary. Sandstone consists primarily of quartz. It's formed by pressure and cemented action of silicon oxide, silica, uh, calcite, calcium carbonate, iron oxide, or clay. Limestone, it's a sedimentary rock. Now, the only thing I can imagine would be you might name a rock a sedimentary rock, and sandstone, limestone, uh, and the most common rocks are shale, sandstone, limestone, and dolomite. So you might keep that in mind. As indicated, the degrees of strength and hardness of sedimentary rocks are variable, and engineering use of such rocks vary accordingly. Relatively hard shale makes a good foundation material. Sandstones are good construction uh, materials. Limestone, dolomite, if strong, can be both good foundation and construction material. The next type rock that they talk about, we've gone through igneous, sedimentary. This is metamorphic, and rocks they're much less common at the Earth's surface than are sedimentary. They're produced when sedimentary or igneous rocks literally change their texture and structure, as well as mineral and chemical composition, as a result of heat, pressure, and shear. Granted, I'm not going to read that, I'll let you, but I would familiarize myself with the metamorphic rocks. the igneous rocks and the sedimentary rocks. Let's move on to weathering and soil formation as a result of weathering. Uh, we'll get into this a little bit deeper. There's mechanical weathering, and then there is chemical weathering. I want you to kind of to be a little bit aware of what they are. Mechanical is more of a uh, denigration of rocks into small particles by temperature changes, frost action, rainfall, running water, wind, ice, abrasion, where rocks are rubbing up against each other, and other physical phenomena. Uh, that these cause rock disintegration by breaking, grinding, and what we're getting down to is soil after a while. I'll let you finish reading that, but I want you to know the difference. I want you to know about mechanical weathering, and I want you to know about chemical weathering. This is decomposition. This is decomposing of rock, which can drastically change its physical and chemical characteristics. This type of weathering results from reactions of rock minerals with oxygen, water, acids, salts, and so on. It may include such processes as oxidation, solution, and strictly speaking, it says solution is a physical process, but it's under the chemical weathering. Carbonation, leaching, hydrolysis, these cause chemical weathering actions that can increase the volume of material and thereby cause subsequent material breakdown. And two, it can dissolve parts of rock matter, yielding voids that make remaining matter more susceptible to breaking, that becomes porous. Uh, and three, react with the cemented material. Just know a little, jot down some notes about chemical and weathering, chemical weathering versus mechanical weathering. Moving on, let's see, where are we? Right here. Here's they call it the process, the geotechnical engineering principles and practices. Uh, uh, Reprinted by someone, but this talks a little bit. I think we'll get to a little bit more, uh, a little more detail, but it's the illustrating is the igneous going to the metamorphic. We touched on that and about how that happens. It involved the iron, I forget exactly. And then the metamorphosis from sedimentary going to, I'm sorry, the sedimentary move into metamorphosis, and then sedimentary move into soil. And we'll get into like what kind of soil comes from sedimentary rock, what kind of soil comes from igneous rock. I don't think we talked too much about the soil coming from magma. Uh, I would think that's a lot more porous, but I don't know. So the type of soil, maybe we'll get into it now. The type of soil produced by rock weathering is largely dependent on the rock type. Of igneous rocks, granites tend to decompose to silty sands and clays. Okay, now we know that the type of soil produced by rock weathering is largely dependent on the rock type. So the igneous rocks, like granite, tend to decompose, produce silty sands and sandy silts with some clays. You know, if you tell me that, I'm good to go. That's what type of soil comes from igneous rocks. So it talks a little bit more about that. Weathered limestones can produce a variety of soil types, with fine grained ones being common. So you may get into clays and things like that. There it is, clays and silts. Uh, I don't know how to pronounce that. Uh, but it's part of the what comes from metamorphic rocks is this stuff and this stuff. Okay, generally decompose to form silt and sand soils, whereas slate tends more to a clay form of soil. So, like for igneous, what do we got? You know, just jot down a couple of things that you can recall. Deposits, where does this soil go? Where does it stop? Where can you find it? Soils produced by rock weathering can be categorized according to where they are ultimately depositive relative to the location of the parent rock. Uh, where is this silty stuff from igneous located relative to the igneous rock? Some soils remain where they were formed, simply overlying the rock from which they came. So they cover themselves up. These are known as residual. Residual just means leftovers, they just stayed there. You get into some more, here they are again, have a general characteristic that depend in the rock type. In the, excuse me. Sorry about that. So let's see. Residual, they kind of stay where they are relative to where they were formed. They're transported soils, and you can assume that these are formed when rock weathers at one site and the particles are moved to another location. Some common transporting agent for particles are gravity, the weight, they just fall apart. So running water for sure, creeks, rivers, glaciers, glaciers, we'll get into that a little bit, and wind. There's a question on there that's going to ask you to talk about. Uh, I think in the test I took out uh, the don't take this to the bank, but the alluvial, and those are important. Those are mostly transported by water. But I want you to know a lot about gravity deposits. Uh, I'll go ahead and talk about alluvial deposits. I think that kind of means water. Alluvial deposits, having been transported by moving water, are found in the vicinity of rivers. Rainwater on land areas runs over land, eroding and transporting soil and rock, rolling the pebbles up all the way up to boulders, uh, depending on the flow rate of the river. Says rivers are capable of transporting particles of all sizes, ranging from fine silts and suspension, like clay would be, to, in some cases, boulders. The greater the velocity of the river flow, there's a question asking you the relationship between the velocity of flow of a river flow, particles, and how they're transporting. So the relationship between river velocity and the size of particle carried also affects the manner in which particles are deposited. And that has to do with the speed of the flow. As the river velocity decreases, relatively larger particles settle quicker and are deposited first. If the velocity decreases further, the next larger size particles settle out. Alluvial deposits are often composed of various soil types because of different types of soil tend to mix as they are carried downstream. The nature of soil can be greatly influenced by past alluvial deposit. Let me see what this says. For example, at a location where a river's velocity decreases as when the channel widens significantly, so the water slows down as the channel. That's like a flow rate back in hydraulic. As it widens, or its slopes, its slope decreases. It's not going downhill like you might see in the mountains. Decreases. Coarser soil particles settle, forming submerged, flat, triangular deposit. I bet you if you saw a creek running into another creek uh, near you, you would see that triangle if the water was clear, where one's flowing into another. When flooding rivers, which normally carry a heavy sediment load, overflow their banks, the overflowing water experiences a decrease because it's in velocity. Then the larger particles, such as sands and gravels, tend to settle more quickly. We don't talk a whole lot more about that, but you can look. Uh, you can imagine an old channel slowing back down, having and the new channel. Uh, if you, I don't. This right here is not uh, on the test. Uh, let's see. Sediments deposited at the mouths of creeks and rivers flowing into lakes, bays, or seas are known as deltas, and we talked about that, like the Mississippi Delta. Uh, and has formed a huge land mass. You will have a question about glacial deposits. Of course, they come from glaciers. Many years ago, over 10,000. Let's see, I think I have that kind of narrowed down so I don't have to read so much. But let me see if I can find it here on some of the notes I took. Glacial deposits result from action of glaciers as from the finest glaze to huge boulders were picked up and transported as they were being carried by glaciers. Soils and rocks were mixed together, thrashed about, broken, crushed, and so on by enormous internal glacier pressures. Consequently, glacial deposits can contain all types of soils. The quality of soil in a glacial deposit is as foundations and construction material is somewhat variable because of the different types of soils. And now we have wind deposits. Wind deposits, also known as aeolian deposits, obviously have wind as the transporting agent. Am I there? Maybe I'm not there in the book, but I'm there in my notes. Let's see. Here they are. So so the wind deposits, also known as a or Aeolian, I forget the thing, deposits obviously have wind as the transporting agent. And wind is a very important agent in certain areas and has the potential to move soil particles over large distances. Fine-grained soils can be airborne over long distances. Just think about out in deserts by wind. Silty soils are more amenable than clay soils to wind transport. That means they're easier to transport by the wind. However, because a clay soil that does bond and has cohesion reduces its wind, it sticks together more so than a silt would. I want to look back here. Write this down. Why is the study of soil as it relates to construction important? Well, that's an obvious one. Rock weathering and soil formation. Under that, we got soil particles are the result of weathering of rocks and organic decomposition. Weathering is achieved by mechanical and physical, by mechanical, which is physical, and chemical means. And I'm going to ask you to describe those two means of weathering. Another thing, found this on page 3. It shows that cycle of weathering. We looked at that. uh, of weathering of rock into soil, and then consolidation of the soil under pressure and heat to form back into rock, and then the weathering of the rock back into soil, and so on. This cycle is known as the geologic cycle. There it is. Figure also shows the processes in the cycle that forms igneous, sedimentary, and metamorphic rocks. What types of soil formed from weathering of the following rocks? And that's the question. What are the types of soils that form from igneous, limestone, and metamorphic? Remember going over that? I hope so. Sandstone, sandy soils, limestone, variety of soil types, fine grained one being most common. So go back through there and know about these deals. There's a one, what's the difference between residual and alluvial soils? Alluvial soils we've kind of talked about a couple of times. They're transported by water, rivers. The residuals usually stay where the parent rock was that they were weathered into soil from. So I've got this to talk about gravity deposit, glacial deposits, and wind deposit. Describe each of these three modes of transporting soil particles. Uh, you know, I don't expect you to elaborate much, but I would take me some notes. Go in your book and find these things. Hopefully, you can pause this video and slow down. There's one more thing I wanted to talk about to get you going. I'm going to try to get something in there from the, let's see, where is this thing? Let's see if it's popped in here. Not there. I want to try to get some group index. We're moving quickly into the actual classification of soils, and we've got a lot to do in these next 4 to 5 weeks. So look at that formula at the top. This is the way to calculate the group index. You saw that guy, and I don't know if you've seen these videos yet, but you will see a video of going through this thing. But this is the final step in classifying a soil in the AASHTO classification system. You have to determine the group index, and the group index, usually the lower it is, the better the soil is. I can't tell what this 15. Okay, I've got these lines in the way, but this is your formula right here for calculating group index. And the F, it's got a little, it says 200, but F is the percent of particles passing the number 200 sieve. Now the 35 is just a constant. So if you had 37% of your particles passing the number 200 sieve, 37 would go in here. Notice it's in parentheses, and then these are in parentheses, and this is a bracket. So we will learn how to deal with this. So look at this right here. You have a parentheses here of 0.2 plus 0.005. All of these numbers are called constants, and they will remain the same. But now when you get to this, what goes in here, this is your liquid limit. It could be 40, it could be 30, it could be 20. But whatever it is, you would insert your liquid limit right here and subtract 40 from it, and that would be the number that would go in here, right here. Liquid limit minus 40. You would actually take whatever your liquid limit is and subtract 40 from it. Whether it comes out a minus or not, doesn't matter. It just goes in here. And then there's this addition right here. Now, this is kind of a dividing point, if you will. It's this stuff plus this stuff actually is what equals the group index. So here you would have, this is a constant, it stays the same, but look again, you have what is your percent passing the number 200 sieve minus 15. Over here is minus 35. And what is your plasticity index? Well, it's going to be given, or you're going to have to find it. And the way you find uh, the liquid, you take the liquid limit minus the plastic limit, and that gives you the plasticity index. We will get to that in time, in a pretty short time. I'm just giving you this to start getting your head right, so to speak. Says as we will be kind to classify soil in the lab. No, we're not. Thus, we will use results of some tests. We will always have, we don't have labs and we're online, so we will take results that I have accumulated to do these things with. So the tests include liquid limit, plastic limit. Those are all Atterberg limits. Remember, you may have remembered this from your certificate program days. You know, you have your liquid limit, and then you have your plastic limit, and that's when the soil changes from a liquid to uh, maybe a plastic to a solid. That's the real basics of it. This we won't do classification. This system based upon the observed field performance of soils under highway things. Soils which have general load carrying capacity, bearing capacity, and serviceability. These will be your soil types. All of these A's will be pretty good soils. They start getting to be a little bit shaky when you get into A4 through A6, and A7 is just a clay, real fine soil, not good for construction. But A1 is the best, and then it says what is the group index. It's to check the quality of the soil. It's a term. Group index is defined as the higher the group index, the weaker will be the soil. I think I said that a while ago. A soil having a group index of 20 is considered as poor soil overall. Here's the formula once again, that F is your percent passing the number 200 sieve. This is 35 is a given. This is a given. Your liquid limit will either be given, and you subtract 40 from it, and when you get down here to the plasticity index, if it's not given, you take the liquid limit, which is given, minus the plastic limit, which should be given. But there's some rules about this that you can go over. Don't know if you have the ability to print, uh, but here's what these analyses follow. Number 4, sieve. This is like a what is this? Is this going to be? Here's a practice thing, and here's the calculation of it right here. It's not calculating this for you, but it's telling you the result is our soil is A76. The group index was 13, as you can see. This might come in handy to get you a little bit on track, but we will cover this quite thoroughly in week 7, and probably more in week 8 and 9. We will end up into the Atterberg stuff, the more plastic kinds of soils. So we'll see you in a bit.